So in order to flip-flop x and y, or sorry, in order to resolve this one, you have to use one of the log properties to undo the log. The two properties we talked about for logs, how they undo one another, was log base b of b to the x is x, and excuse me, b to the log base b of x is also x. That's how you undo a logarithm, or how you undo a base, if you will. Okay. Now, in this case here, I need to get rid of that log base 9. So I 9 both sides. What I mean by that is I'm going to exponentiate this one up. By putting this here, it undoes it. By putting this here as a base to the exponent of x, it's keeping it balanced. This simplifies, and all you're left with 9 to the x is y. Remember, log form and exponential form are inverses of one another. So if you just rewrote that as an exponential form, it would have been correct. Because that's what that means. Right? When you have the one up here where it was 62, the natural log, when you have the natural log of, so it's y equals natural log of x minus 1, you do the same thing. Remember, natural log stands for log base e. So whenever I have natural log, I'm going to rewrite it as log base e. Change x and y. It's the same idea. I need to undo the log. How do you undo the log? You e it. By doing that, it undoes this base, allows the stuff in the parentheses to fall. Now I have e to the x. You're just using those separate properties. See what I'm talking about? It is e. And there you go. That's all it means. That's all it means. Oh, we go back. What you would do is you change the base of the 49 to be a base 7, so you can do that. Yeah. So with that one, you've got y equals the log base 7 of 49x. In order to make any of that work, you got to get that 49 to have a base 7. So we know 49 is 7 squared, so you would just write it as 7 to the 2x. Okay. Then you 7. Well, sorry, I have to flip. Then you flip flop. Then you would wind up 17 it. You're exponentiating both sides. So you get 7 to the x is 2y. So you get 1/2 7 to the x is y. Oops. 60. That was 60, correct? Okay. And remember. Oh, yeah. I'm sorry. I overlooked that. Yeah. I'm sorry. Yeah, it winds up in the one. I'm sorry. Thank you. I didn't even recognize I had written that. That's when I got rid of that base there. It does it right away. Thank you, Colby. I didn't even. You get x equals 2y, so it's x over 2 is y. Sorry. Thank you, sir. Yeah, we're like, whoa, someone got a little crazy going there. Oops. Graphing. Whenever you're graphing, remember the trick, and we kind of alluded to this towards the very end of the period yesterday. The trick is that you only need to come up with one number on your own, and that number that you figure out on your own is what is the base that you're dealing with. Okay. Because as you're looking at your ordered pairs and stuff, you get, let me pull this back up. As you're looking at 66, remember, this is the exact same thing as saying log base e. Okay. E's approximation. E is like 2.8-ish, I think is what we said it was. So when you go to when you go to graph these, whether it's an E problem or it's just log base 4, it doesn't make a difference. Your parent function will always be y equals log base b of x, and then your shift is basically x plus h, y plus a, whatever those values may be. Okay. So when we did this yesterday, we kind of ran through it quickly. Yes, sir. Plus or minus. I'm just saying whatever those values are. Plus or minus h. How about if I write it as plus or minus h or plus or minus k, depending upon what it is? Does that make more sense? You're just shifting it left or right, up or down. Sir. Parentheses. H's will always be in parentheses. K's will not. Even if it's natural log. Because natural log is just log base e. All they're doing by writing it as natural log is they're saving ink. It's less letters. They cut it in half. L-O-G-E-L-N. 2 letters, 4 letters, half. That is out. He's like, screw this, I'm going. So when you do this, you're ordered pairs. Remember, you have 2 properties. You have log base b of b is 1, and log base b of 1 is 0. Those are the 2 properties that will generate your ordered pairs, no matter what the function is. Whether it's a natural log function, a log base 6, log base 2, log base 1/2, it does not matter. So your one ordered pair is always going to be b and 1, and the other one will always be 1 and 0. No matter what, your 2 ordered pairs for your parent. I didn't say poop. Anyway, they turn on you quickly here. You don't turn on each other. He dropped an F-bomb the other day. You guys didn't even phase. Jeez, I say shift. And you guys are, ooh, Vermia. Yeah, right. That's good. That's funny. I thought it was funny. That's why I laughed. Whatever. Anyway, so when you have E, E is just an approximation. E is like 2.8-ish, somewhere in that neighborhood. So if you're going to graph this one, in this one we have your base is E, your H is 0, and your K value is +3. So all of these points are just they're gonna stay at the same horizontal position. They're just gonna move up 3. Okay. Now when you do this, remember you're you're gonna get a vertical asymptote at whatever your H value is. Your parent function always has a vertical asymptote at 0 because your H value is 0. And it just so happened that this problem also has a vertical asymptote at 0. So it's no big deal. So your ordered pairs then become E and 1, 1 and 0. The shifted ordered pairs would just be, well, there's no left or right, so I have to change the x, so it's going to be E. And then I have to move it up 3. And those would be your ordered pairs at the bottom. That's it. Get to. That's what I didn't like about the textbook. They didn't give you any problems with both. I'm going to give you 2 problems that have both in it tonight. Colby, you're welcome. Yeah. So your parent function, E is 2.8 something. So 2.8 and 1, so it's here and here-ish. And then 1 and 0. It's doing that. The shifted function still has the H value at 0, so you still have your asymptote at 0. Your new ordered pairs were at E and 4, and 1 and 3. and it's just doing this. Your domain, all real numbers greater than 0. Your range, all real numbers. Get what? X and Y. That's all it is. It is graphing logs are just ridiculous. And there's really not much to it. For range? Because there's no asymptote. There's no horizontal asymptote, like a floor or a ceiling. Yeah. Domain is all your X values. Because there's a vertical asymptote, it's everything to the right. Yeah, your domains for all logarithm problems, whether it's log base E or regular logs, it's always going to be, your domain will always be X is greater than whatever your H value is. Always. That never changes. Other than that, those should have been pretty quick, right? Simplified, those are easy, right? Good, because you're going to use some of that stuff today. So what we're doing here today is, excuse me, let me save this one real quick. I was talking with the pre-calc teachers and the honors pre-calc, Ms. Denny, about how far and in depth that they really need to push into, what do you call it? No, I don't want to do that. Don't die, Devin. Sorry, I gotta save this one. Can't have two of them open at the same time. Anyway, so when I was talking with Ms. Denny, Lascota, and Lofthouse, and even Fontana, a lot of the stuff that I've done in the past with logarithms is I've gone really crazy into the more complex condensing and expanding of logarithms. And in all honesty, you don't need it. So we're going to cut back a little bit here because I'm really running short on some stuff. So we're going to be done with this on Friday. Okay, I've already put that on the calendar and all that. Yes, sir. Logs. They're big, they're heavy, they're wood. Okay. So we'll be done with all this. I had to change that up. I didn't get a chance last hour to do that. But what happens here is that these three properties that we use for either expanding logarithms or condensing logarithms are super easy to work with. And their main purpose to use them is so that way tomorrow when we solve equations, we know how to group things cleanly. All right? It is super fast. So you get these three properties. When you have a log with the same base and you have two values being multiplied together, you can split it apart. So log base b of u times v, it's on the board. It splits apart to two addition problems. And the reason that we do this is because sometimes you can simplify one of the logs before the other. It's a means to get to, not means to, yeah, it's technically, you're right, it's a means so that way you will be able to in fact solve an equation tomorrow because you work backwards that way. All right. So you can split apart multiplication problems into two logs via addition. You can take division problems and split them into subtraction. And once I put these things together with specific values, you'll see what I'm getting at here. It is really easy to work with. And then the last one that we talk about is when you have a log that's raised to an exponent, or I'm sorry, the log itself has an extra exponent to it. You can move the exponent out front. So you can move this up just a bit. Oops. You have log base b of u to the n. And when we put this stuff together with some numerical and some variable style problems, you guys will be like, oh, well, that's really easy. And don't freak out like, oh my God, it's so hard to figure out what to do. Whoa. Because a lot of you right now are probably thinking that in so many words. Once you realize that multiplication is repeated addition, Division kind of looks like there's a subtraction symbol between, when you have a fraction bar, it kind of looks like a subtraction thing. Really, all you have to kind of remember is that the exponent comes up front. Other than that, it will be rather quick to work with. For example, when if I look at, let's do these one at a time. If I do a numerical one first, I'll show you a couple of ways we can go about this. If I have the log base 3 of the quantity 3 times 9, that means I can take that logarithm and split it into 2 separate. Okay. Why would you do that? Just showing how the property works. Like I said, the reason that we want to be able to do this is so that way tomorrow when we do equation stuff, it simplifies the equations. What's log base 3 of 3? 1. And then how do I rewrite 9 as a base 3? 3 squared. What's log base 3 of 3 squared? What's 1 plus 2? It is an awfully weird way to write 3, isn't it? What's log base 3 of 3? Log base b of b is always 1. So log base 3 of 3 is, remember, that means 3 to what power is 3? 3 to the first power is 3. Okay. Same thing goes for, if you think about it, couldn't this be, if you did order of operations, isn't this the same thing as saying log base 3 of 27? What's 27 as a base 3? 3 cubed. So that's the same thing as log base 3 of 3 cubed. Well, isn't that the same thing as this one here, we have log base b to an exponent? So isn't that 3 times the log base 3 of 3? Which isn't that just 3 times 1, which is still 3? Log base 3 of 3 cubed is also just 3 because bases undo each other. Yeah, there's a lot of different ways to simplify these things out. Okay, there are a lot of different ways to simplify them out. Okay. All right. What about log base 3 of a third? That's a division symbol, isn't it? So it's subtraction. It's that thing. So that's the same thing as saying log base 3 of 1 minus log base 3, 3. Well, according to my properties, log base b of 1 is 0, and log base 3 of 3 is, what is 0 minus 1? Now, isn't 1/3 as a base 3 the same thing as 3 to the negative 1? It's the same thing, isn't it? Right? Coincidence, right? All right. Same deal here. I do log base 5 1/5 to the third. Oh, that's really cool. Sorry for those of you with bad eyes. The log went for a jog. It turned. Anyway, so log base 5 of 1/5 to the third. You can do a couple of different things here. Isn't 1/5 5 to the negative 1? Okay. I can do it that way. Or can I write it as 3 times the quantity of log base 5 of 1 minus log base 5 of 5? I could, couldn't I? Is there one way better than another way? Yes, ma'am.
Don't you also do the bottom one and log 5? Just like it is on the bottom.
Oh, by writing it. Yeah, that's what I did. Yes, but I did that here, and then I split it. So I skipped that step. What I did, what you're saying is absolutely right. 3 log base 5 of the 1/3, excuse me, 1/5, then simplifies to be that. So you're right. I just did that in one quick step, but you are absolutely right. You're absolutely right. What's log base 5 of 1? And log base 5 of 5? 0 minus 1 is? 3 times -1 is? Look at the excitement back there. Look, you two are getting along. That's weird. I'm turning around, she's going to smack you. Yeah, right. All right, so what happens when I ask you to take this and expand it? When I go to expand something, that means I'm going to split it into multiple logs. It's like I'm chopping a tree. I'm making more logs. Log stands for logarithms. Logarithms are used to solve for variables and exponents. Because like we did this yesterday, 2 squared is 4, 2 to the 3rd is 8, 2 to 1 power is 6. No, I think his name was like Frank something. I don't know, he was sitting on a log when he figured it out. They're big, they're heavier wood. So when you have this, notice you guys, you'll see that there's multiplication, there's an exponent, and there's also a division. My suggestion to you guys when you write these things out, if you have multiple parts to it and there's a division at the end, put everything in the numerator, obviously first, grouped in parentheses, and then divide out by everything in the denominator. Because sometimes the denominator might have 2 parts where you'd have to have a grouping symbol to have those put together. Does that make sense? I'll show you what I mean as we get to it, but we know that this is going to be log base 2 of 7, and then it would be a plus a log base 2 of x cubed. But can I shortcut that and write as 3 log base 2 of x? Or 7 times x cubed? When you have the same base, multiplying, you just split apart with the addition. That's everything in the numerator that I subtract log base 2 of y. Yeah, I hadn't gotten there yet. The only thing that's left that I could do is just move the exponent up front, because then it would be fully expanded. And by all means, if you want to do that right off the bat, go for it. There's no rhyme or reason why you can't. All right. And we go from there. It's because it's divided by y, so that means the last part is you're dividing the whole thing by y, so it's minus that last bit. Oh, see how it's got the log base 2 of x cubed? When you have an exponent after a log, I can move that exponent in front of the log. The property tells me so. Right? I don't know. So if I have the log of xy squared, what's the base? Do I have to write 10? Nope. And remember, the reason that we have the common log stuff is because the calculators, I would only say it's about 3-4 years ago, maybe 5 years ago, started being able to do what we call change of base. It's actually, this textbook shows you how to change the base for people back in my day. We actually had to use log tables and do long multiplication. Multiply 4 digits together by 4 digits with decimals. It was awesome. You guys have it so easy. So, again, do I need to write base 10? If you do, are you wrong? Nelson likes it. She's like, this is nice. Yes, sir. Yes. Does anything change? Let me ask you this. Do you believe that anything will change? If I ask you to do it's log base E. Do I have to write it as log base E or can I leave it as natural log? I can leave it as natural log. It does the exact same thing. With log base E, they all share the same base. It's fine. Don't have to worry about it. So if I wrote that one out, I can write it as 3 natural log x plus 2 natural log of y. Throw it in parentheses. Subtract the natural log of z. Uh-huh. That's what it is. They use that's what they use for natural log. They use the lowercase l. No. It's log of the natural. It's yes, it got fancy and they just got some like, oh, this sounds stupid. So they put it as natural. They put it as natural log. Okay. All right. Condense. Take multiple logs, make it into one. You're bringing super glue. It's fun. It is, and when you're condensing them, you don't see it as often in parentheses, especially with numbers, because when you're multiplying, even with division, you're just multiplying straight across. That's why it's not really that big of a deal when you put it all back together. I do that by throwing it in parentheses, especially if there's 2 parts to the denominator. You normally don't see it if there's just 1 part in the denominator. So if I have log of 6 plus 2 log of 2 minus log of 3, again, this is one of those that has the common log. They're all base 10. So by putting it all back together, we get log of 6 times 2 squared over 3. You all right? You kind of went across that out there, all right? Okay. Whenever you see the plus sign, that means that 2 parts next to each other are being multiplied. Whenever you have a number in front, which means it's an exponent. So when we have the 6 plus the 2 log 2, that means there's a 2 squared times 6. Okay? Yes, ma'am. I haven't got that far yet. What? Jordan just asked about that. Just so everybody hears this again, a lot of times they don't put parentheses around the front 2 when there's just 1 part of the denominator. There's 2 parts of the denominator, you usually will see it. So let's see, we get log of 8. Done. And you go to the next problem. It's condensed. It's milk in a cake. Yeah, condensed milk. You missed out on good jokes yesterday. Oh, so never mind. All right, what do you get for that one? Did you get?
Yeah.
All right, if you wrote x to the 1/2, that's fine. Now, in all honesty, the reason that we're doing this, so that way you guys see how the exponent stuff are going to work and why we work through in this way, is because when we get into equations, I'm trying to find a good example. As we get into equations, you're going to have to as you get to equations, you have to sometimes condense one side prior to doing anything else. That's why we show these two properties. Okay. Now, looking at just this monstrosity of a problem here, what do you think you could do to the side of to the right side? What you're saying simplify? What would I do? You said it. Divide it. So I would condense the one side, and I would get natural log of x plus 5 equals natural log of x minus 1 over x plus 1. Oops. And I get that. What does natural log stand for? Log base e. So how do you undo the natural log? You e it. So if you e both sides, you get x plus 5 equals x minus 1 over x plus 1, and go on from there. And then you would go on. But that's the reason why we are setting these things up today with this condensing and expanding. So that way when you see something like that tomorrow as we build into it, it's so much easier how to work with it. Because if we understand these really simple properties, we'll be able to solve equations rather quickly. Okay? That's the reason why we go through these things. Okay? That's just fraction equal fraction cross multiply. Remember that fraction equal fraction? Just cross multiply. Little trick that I showed you a couple times. What was the other one I was going to show you real quick? Do this. I'm guessing you probably think, or do you think you have to expand or condense that? Condense. Why do you think you'd have to condense it? Because there's a lot of logs going on. So if there's more than one log, it means you're going to be condensing. If there's one log, you're going to expand. I try to make it sound something. That's not working. It'll tell you. It is pretty blatantly obvious. If there's more logs than you know what to do with, make it into one. If there's one log, make it into multiple. Can't do it. Because the rules are that they have to have the same basis to make a lot of stuff work. So all of these rules here, they all have the same base. If they don't have the same base, it's not going to work. And that came up with the idea of why they had to do all these change base formulas, which we don't even have to worry about anymore. This is a button on the calculator. So if I start looking at this one, you start with the first group of parentheses. You got natural log of 3 minus natural log of x. That tells you you have 3 over x. You okay with that? That also tells me that I have natural of 3, well, we were right here, 3 natural log of 3 over x. What do I do with that 3 then? I cube, yeah. So I'm just going to continue everything on the one side first. So I get natural log then, it'll be 27 over x cubed, I believe. If I cube that whole thing. What's that? Because this is right to this parenthesis only. Property. See how I condensed on the inside here first, If I just write in 3 over x, this 3 is still out in front of it. So remember, if it was 3, this 3 log of u means it can come back up to an exponent. See where I'm going with that? Anytime you got a number in front of a log or natural log, it's an exponent of what's after it. So then you get the other side. What is that? X over 9. So putting those back together, let's see, that means we get natural log 27x over 9x cubed, which is the log of 3 over x squared. Yep. Well, that's a real weird way to write 3x squared. Oh, sorry, 3 over x squared. You can get some pretty crazy looking stuff that simplify out to equal like 2. What? It happens. What's that? All natural logs are weird. All this nature. It's a random stuff. I don't know if it was a pity one or what. Yes, ma'am. It is a multiply. I multiplied straight across. 27 times x cubed times 9. I just put them together because they're still fraction over fraction. When you have when you're multiplying fractions, you just multiply straight across. So let's see here. I often wonder how many files I actually have on my computer. Probably more than that.
More than just one.
You're probably right.
Yeah.
The answer is 6. Log base 4. So here's what I have you guys do tonight. You had asked about why isn't there any graphs with H's and K's? Well, there you go. I made up 2 graphs of H's and K's. Merry Christmas. You're welcome. So you'll have to write those down because I have not written those. It's kind of hard to write subscripts in the Google Calendar, so there's that. But then the other part is the 30 through 54 in section 8.5 to every other even, as well as 56. Because as you get going into these things, they're really quick. I think really the only 2 that might be a little bit weird might be 54 and who's the other one? What was it? Yeah, 56. I know 56 is a little bit weird if you're not careful. But if you followed through what we did on that last example with the natural log stuff, you'll be okay with 56. Okay. Tomorrow we'll knock out the equation stuff, and it should go rather easily. Make sure your calculators are charged because a lot of the times tomorrow we will need to use the calculator to solve some stuff out, just so you guys are aware, and go from there. Locally, dokally. If you start at 30, you end at 54 with every other even, but I wanted you guys to do 56 because it's a little tricky. Yeah, there's not much. And then when you're doing, oh guys, when you do the graphs of this one, just when you graph it, make sure you graph your your parent ordered pairs, and then write down your shifted ordered pairs, and put down, where your asymptote is, stuff like that. You don't have to make it super beautiful, just to let you know where your parts are so that we can label it. Because a lot of times that's all I ask you guys to do on tests and things are label your parts. Because if I don't let you have a calculator to figure out, oh, what's E, I'd have to make sure you know how to find, well, I'm going to use 8. Okay. It's got the double snap fingers. See you later. Joke. It's a tough crowd here. Tell you. I am not going to give you the satisfaction. You had your chance, and you whiffed. You whiffed on the chance.